Welcome, pre-calculus students. Today we're going to be taking a look at finding zeros of polynomial functions with a degree greater than 2. We've looked at quadratics, we maybe even done some cubics, but we're really going to examine what happens when we get some polynomials with really high orders of degrees. First of all, a complex polynomial of degree n always falls in the form p of x, the polynomial, will equal a sub n x to the n, that's why the degree is n, because that's the highest exponent, plus, we're going to move down the line, a sub n minus 1, x sub n minus 1. We're going to keep adding all the way down to get a sub 1, x sub 1, plus a sub 0. This just means it's a constant. I know it's a crazy form, maybe you've seen it before, maybe you haven't. But the important thing to know is that all of these a sub n minus 1s, a sub 1s, a sub 0s, these are just coefficients. They're coefficients that are some complex number. Could be real, could be imaginary, but all we need to know is that they're complex numbers. The fundamental theorem of algebra says that for every function with a degree of at least 1, so that means your degree, in this case n, has got to be at least 1, it's bigger than 1, has at least one complex 0. That means that no matter what the function we have, no matter what the polynomial is, there's at least one place, whether it's real or imaginary, where that thing will cross the x-axis, will be at least 1, 0. The linear factorization theorem says that it kind of takes the same idea, but it goes at least one step further. It says if p of x is a function with degree of n is greater than or equal to 1, so again it's at least 1, it's bigger, then p has exactly n factors, and can be written in the form p of x equals some constant times your first factor times x minus your second root, all the way down. We're going to keep multiplying them together until you get subtract some constant, the nth one. So what it's saying is that if I take a function, something like, I don't know, f of x equals x to the 14th plus 5, we can write this as some combination of complex and real factors with 14 different factors, because that's our degree. The only thing we need to know is that C1, C2, C through N, all these numbers, they could be complex numbers. They're not necessarily real. They could be complex, but we know that there's at least n of them. If one of these factors occurs m times, then it's said to have a multiplicity of m. So for example, if we could take a polynomial function and say that it's equal to, I don't know, x minus 5 times x minus 2 times x minus 5. Because this x minus 5 is repeated twice, we'd say it has a multiplicity of 2. You can see this because if you go to rewrite it, we take x minus 5 squared. That exponent on the factor is what its multiplicity is if it's ever greater than 1. The next thing that's going to be helpful in solving all of our zeros is understand that complex factors must occur in conjugate pairs. It's kind of a crazy way of saying this. Complex factors. So if we have something like, if one of our factors to our solution is x minus 3i, it's complex, it has an imaginary number, then we know its conjugate pair is also one of our factors. Conjugate pair of that would be x plus 3i. Another way of saying that is if one of our zeros is an imaginary number, I don't know, something like if x equals 4 or 5i, we would also know that x equals negative 5 is also one of the solutions. We'll take a look at it why later, but you need to know that again, complex factors come in conjugate pairs. If you have a positive number with an imaginary number, then you also have to have that negative one. Finally, last piece of vocab. If a polynomial has degree n, then it has exactly n n zeros, where we'll count them for a multiplicity of times. So for example, we could say if x to the third plus 4x minus 5, this has a degree of 3, so we know there are 3 zeros. Some of these may be complex, some of these may be just real numbers, but we know that there's going to be 3 zeros. Something that I'm looking back up at this complex pairs come with conjugate pairs. complex factors must occur in conjugate pairs. Something that may help understand is this isn't just when there's i's by themselves. So for example, if you have 3 plus 2i as a solution, then you need to have 3 minus 2i as one of your solutions as well. We're going to go now take a look at a couple examples and how this helps explain, maybe put a little more context to some of this vocab.